Yeah, I think people are joining. Uh,
Okay.
yeah, so this week we will have Hyeonho to present his working video. So Hyeonho is a graduate student at KAIST AI, and his research focused on controllable video synthesis and video editing using diffusion models. So Hyeonho, I will pass it to you.
Okay. Good morning, everyone. I'm Hyeonho Jeong, and thank you for having me to give a talk to this group at University of Waterloo. And in this work, I will introduce like several works on diffusion-based video editing and generation. And instead of diving into minor details of each work, I will try to share my perspective on the problem settings and precise insights of the proposed solution. Um, Before we start, I would like to share a bit on myself. I majored computer science for my bachelor's, and since last year, I've been pursuing master's at KAIST in South Korea. And this summer, I was lucky to have done internship at Adobe London Lab, and recently, I got a full-time offer from Adobe, and we're joined there as a research engineer after my master finishes. And also, this is my group in KAIST. Yeah, it's like a huge group. Our group has always been working on diffusion-based generative modeling. So now let me start with my project called Ground of Video, which I presented at iClear this year. Uh, Very simply wrapping, this is the first work that brought grounding conditions to video editing and still a very powerful framework for complex multi-attribute editing of videos, even though it's based on an image diffusion model. So at the time of this research, there were no publicly available video diffusion models, like unlike nowadays. As a result, prior works and concurrent works at this time had to rely on stable diffusion to perform any types of video editing. And naturally, there were several limitations. So temporal consistency of the generated videos were pretty disappointing. And here by temporal consistency, I mean these noticeable flickerings and appearance inconsistencies. Another limitation I found was that almost all existing methods become very inaccurate in the scenario of complex multi-attribute editing. So the simple and core idea to address all these issues is to get help from additional spatial conditions to complement the reverse diffusion process. And regarding spatial conditions, I prefer to categorize them in two different types, spatially continuous representations and spatially discrete representations, where most people usually focus on the former only. So good examples of spatially continuous representations are like depth map and edge maps. They are spatially aligned with the input frames or image strictly, and they explicitly provide information about the structure and shape of objects through every part of the image or the frames. On the other hand, especially discrete conditions refer to modalities that do not rigidly dictate the precise structure and shape of objects. Instead, they give implicit hints on the overall layout of the scene and positions of each entities. Specifically, we focus here in this work, we focus on groundings, a pair, and here by groundings, we mean a pair of bounding box coordinates and text description that pertain to the identity inside the bounding box. And the intuition of ground video is to use the best of both worlds to guide the denoising process. Specifically, these three modalities, so depth maps, optical flow maps, and video groundings. Then how can we inject the spatially continuous conditions? to the denoiser unit backbone. Since these conditions are aligned spatially with the input tensor, things are very easy and intuitive. So I'll go briefly here. So first, we warp the initial latent using the correspondence of optical flow maps, which guarantees that the repeating regions across frames share the same pixel values. And doing this greatly enhance the temporal consistency. And second, we use depth maps. And for depth maps, we use control net. We encode depth map features to the latent unit space using control net. And the encoded features are simply added to the original unit backbone features, which give pretty structured guidance as demonstrated in various image editing works. Now, making use of spatially discrete conditions, the groundings, is quite tricky because they are not spatially aligned. In other words, these tensors are in totally different shapes as the input tensor, the input video. But gated attention mechanism solves this issue. So gated attention accepts grounding tokens. So we first need to encode the groundings, the layout information, into grounding tokens, as shown in the right part. And of course, for all the video frames independently. For each transformer block within the unit backbone, gated attention layers are inserted specifically between self-attention and cross-attention layers. And the gated attentions are responsible for projecting the grounding information from the grounding tokens to the original latent features. And this is how the gated attention mechanism operates. In its sense, it is basically a self-attention. The proper frame tokens, the original tokens, which are the outputs of the previous self-attention, are first merged with the grounding tokens. And then all the tokens are processed together in the green self-attention module. After this attention, the resulting grounding tokens are discarded, and only the updated purple frame tokens proceed to the next cross-attention layer. And lastly, since we built our method on a text-to-image diffusion model, the model inherently does not allow any interaction across frames. To handle this, we use a common strategy that is pretty common in video editing projects. So we inflate all existing spatial attentions into spatial temporal attention. And here, by spatial attentions, we mean both self-attention, the original self-attention, and the newly added gated self-attention. So to sum up, this is the overall framework of ground the video. So the left side illustrates the input preparation stage, and the right side shows the denoising process. And as you can notice, ground the video requires quite a few more conditions than other works, but for example, like depth, flow, groundings, but obtaining all these conditions are automated, and thanks to them, ground the video significantly outperforms existing baselines in the scenarios of complex edits. So for example, given this input video, a man walking a dog on a road, so ground the video can easily change the dog into a Lego dog or the person into a Simpson with a great temporal consistency and accuracy, but usually all other works can do this too. And changing the background is also easy. However, like this is like the main contribution of this project. So you can quickly edit the dog, man, road, respectively in a one go, including the case of multiple edits and also including the multiple edits and style transfer. So, and also this is another example, a rabbit eating a watermelon on a table. So single object editing is easy. Well, it can also perform much more complex edits, even 4 different edits concurrent in the same time. This is another result. So qualitative results, simple edit to complex edit to even more complex edits. And This framework can also generate stylized videos seamlessly. Given these real-world videos, it can generate videos that have high fidelity to both the input videos and the target style text. And for the baseline comparisons, we use 20 videos from David's dataset, and for diffusion-based other video editing baselines, tuner video, control video, and the product Gen 1. So qualitative results are shown on the top and the numbers are shown on the bottom. This is another comparison example where the editing scenarios we intentionally made editing scenarios very complex and challenging. And one necessary and emerging research direction is to assess and compare existing video editing methods systematically, because every paper says they are the best using like different metrics and different benchmarks. So here's like a one recent paper called Edit Board, which provides a comprehensive evaluation benchmark for text-based video editing specifically. And in particular, they compare 5 video editing models, including ground-up video, and all these models are text-to-image diffusion-based for a fair comparison. And they split video editing into a few subtasks like single object editing, multi-object editing, and a few more categories. And ground-up video surpasses other baselines in almost metrics and also in most subtasks. Even in their discussion section, they exclude the ground-up video and they continue their analysis. So we've explored what we can do with image diffusion models. Then what creative video tasks can we do in the presence of video diffusion models? So I will introduce my work, VMC, which was presented in the CBPR this year. So before we talk about the specific task called motion customization, which is like the main topic of this work, but let's discuss a bit more on text-to-video diffusion models. So finally, text-to-video diffusion models have been open source, not all, but although and usually the closed source ones are usually very superior to open source ones. So many categorizations exist, but I like to classify video diffusion models into non-cascaded ones and cascaded ones. So non-cascaded video diffusion models are the typical models we normally refer to, like AnimateDiff for stable video diffusion or OpenSora plan. And from Gaussian noise and text prompt as condition, they iteratively denoise and reach clean level videos. And these videos are usually like the final output videos that users get. On the other hand, cascaded video diffusion models consist of several denoising processes from each model, where the term cascaded can simply be understood as a sequential pipeline of experts, where each expert are actually video diffusion models. So they were first proposed by Make a Video and Imagine Video, and the recently announced MovieGen also belongs to this family because this MovieGen employs a spatial upsampler, which is a video diffusion model. So specific details vary by works, but roughly speaking, the cascaded video diffusion pipeline consists of 3 stages. So keyframe generator, keyframe generation, temporal upsampling, and then spatial upsampling, where all these models are again video models, especially video diffusion models. So the initial keyframe generator has a very strong text to video prior and generates spatially and temporally low resolution videos from noise. And then the temporal upsampler performs frame interpolation. In other words, they increase the FPS of the original keyframes. Then the spatial upsampler performs video spur resolution, where the final output video is produced. So the below videos are the example outputs of Imagine Video pipeline. So I'm personally a very big fan of cascaded video diffusion frameworks, and I still believe that these frameworks are quite underexplored, despite the fact that they can easily generate very high quality and high resolution long videos. For one reason why it is not underexplored is that I believe is that there's like a one fatal limitation, which is that the whole process inherently takes a long time. But surprisingly, like acceleration research, like consistency models or progressive distillation models, these research are not being studied on the proper computational bottlenecks as I experienced. So, for example, some few-step diffusion models have been proposed for the video models, but they can be only applied, those methods can only be applied to the initial keyframe generation stage, which is the what we call the general text-to-video diffusion model, and which is actually used only once throughout this whole process. Also, the latence, the shape, the latent size, the tensor size are at this stage are temporally and spatially very small. So even without the acceleration, this inference takes a very short time. However, the later temporal and spatial upsampling stages are applied multiple times to generate just one video. And usually one single inference takes much longer than the first keyframe generation stage. And even worse, so even when equipped with multiple GPUs, this upsampling can't be parallelized, but has to be applied sequentially because they take the previous output as the input. So I personally believe accelerating the video upsampler video diffusion models is like a very practical future work. So now back to VMC. So in this work, we propose the video motion customization framework on top of a cascaded pipeline. But here, what do we mean by customization and like motion customization? So given a subject image for reference, appearance customization like Dream Boost in generative models aims to fine-tune the image models to generate subject images in a diverse context. Like another example is like texture inversion. However, like on the other hand, the given a reference video, the motion customization aims to adapt pre-trained video models to create videos that feature the reference motion concept instead of appearance concept across various visual contexts and scenarios, but without learning the appearance of the input video. So we first make the problem easy with a few insights. So first, keyframes are almost always enough to determine the motion of a whole long video. Thus, if the reference video is temporarily short, we use as is. And if the video is temporarily long, we sample only keyframes and use this resulting sparse video as a reference video. Otherwise, the computation memory won't fit easily to like unless you have super huge GPU. Moreover, that being said, in the cascaded pipeline, we can only adapt or fine-tune the initial keyframe generation model on the extracted keyframes, while freezing the later upsampler models. It's also very important to note that the keyframe space is spatially low resolution space, which makes the model adaptation even faster with very low memory usage. And the second insight is that the temporal tensions are where interactions between frames occur and where the robust motion prior of the model is stored. So to this end, we propose to tackle only the keyframe generation video diffusion model. And within this model, we fine-tune only the temporal tension layers. And this training design leads to two advantages. First, the preservation of the model's inherent capacity for generic synthesis, since most rates are frozen, and including existing all spatial rates like self-attention, cross-attentions. And second, significantly lightweight and fast adaptation. More specifically, the fine-tuning requires only 15 gigabyte GPU memory, where it finishes in less than 4 minutes. However, optimizing the model with the standard diffusion training objective leads to entangled learning of both appearance and motion, as observed in a tuner video baseline and its follow-up works. As an example of this video presented, so airplanes in the output video looks very similar to the sharks in the input video, caused by the entangled learning of both appearance and the motion. Whatever the parameter efficient fine-tuning strategy is employed. So to this end, we propose a new objective that distills motion information of a video V. So our intuition is that the residual vectors between consecutive frames include a huge information about motion trajectories. So given an input video V0, we can sample Vt at any time step t in a closed form using the diffusion forward. Then we define motion vector by frame residuals at time t as in the equation 2. And the epsilon residual vector delta epsilon t is also defined similarly, where we empirically set the stride c as simply 1 here. Then the residual vector delta Vt can be delineated as the equation 3, where delta epsilon t is normally distributed with zero mean and 2i variance. And in a sense, delta Vt can be acquired through the diffusion kernel in equation 4. In the light of this, our goal is to transfer motion information to the temporal tension layers by leveraging the motion vectors. Thus, we first simulate the motion vectors using the video denoiser epsilon theta. Then the denoise video vector estimates V hat 0 can be derived by applying Tweedy's formulas in equation 5. Then the denoised motion vector estimate, the red colored delta V0 hat can be defined in terms of noisy motion vector delta Vt, and the predicted noise, the delta epsilon theta, as in equation 6. So similarly, in equation 7, this blue colored ground truth motion vector delta V0 can be obtained in terms of delta V0 and delta epsilon t. Finally, so this is our objective. So our objective is to fine-tune the model by aligning the ground truth motion vector and its denoised estimate as in equation 8. And by using L2 distance for aligning function, this is exactly equivalent to matching the ground truth epsilon residuals and predicted the epsilon residuals. So to sum up, we fine-tune keyframe generation video model UNet by aligning the ground truth epsilon residuals, the ground truth the noise residuals, and the predicted noise residuals. And once trained in the inference phase, our process begins by computing the inverted latence from the input video through the DDIM inversion. And subsequently, the inverted latence are fed into the temporally fine-tuned keyframe generation model. So the generated keyframes then undergo temporal and spatial upsampling using the unchanged or unmodified temporal and spatial upsampler models. So these are share some results of VMC. So we can customize the motion of sharks swimming as presented in the video to various visual contexts. And we can customize the motion of pills falling. We can also customize the motion of car driving, and motion of car driving can be transferred to a horse running too. And the rabbit eating video again, we can change the various animals and the foods and the background. We can also customize the motion of an airplane and a bird flying. And these are other results. So for comparison, we compared VMC against other baselines, video composer, Gen 1, tuner video, and controller video. So at the time of this research, so this was like one of the very first work in video motion customization. So these works were not devised for motion customization, and there were no baselines we could use, like motion customization baselines. Yeah. So they are just simply like video editing baselines. Yeah. So others face difficulties in like avoiding from the original shape of the subject in the input video, leading to issues like a sharp-shaped airplane. So before we end talk on VMC, I would like to say that the motion customization is high potential in commercial use cases because it allows users to explore their creativity with very high freedom. So for example, Pika Labs recently announced their new tool, like Pika Effects, which is basically applying the customized motion effects to the input image or the user provided video. And yeah, if I were to design this tool, given a foundation video model, I think like one reference video would be enough. Unlike so in the VMC we use a single video, but like I think for this kind of complex level motion customization, I think many reference videos are necessary. Yeah, but for the training objective, I think like other doesn't have to be VMC because there are other great concurrent works in motion customization, such as Motion Director and Diffusion Motion Transfer. I really like both of works, and just to give you a brief summary of other works, how they achieve motion customization. So Motion Director, so to learn appearance properties on the left, so Motion Director fine-tunes spatial layers using image diffusion laws using a reference image. And then to learn motion properties, Motion Director fine-tunes temporal layers using video diffusion laws using a reference video. And upon fine-tuning, they optimize LoRa layers instead of the original attention layers to preserve the original capacity. And in the diffusion motion transfer on the right, they propose a certain objective and optimize noisy latence during the reverse diffusion process, specifically only during the early denoising step. So their objective, the objective they use is quite similar to our VMC objective, but they calculate this loss using the diffusion features instead of the predicted noise. Yeah, so next I would like to talk about the Dream Motion, which was presented in the ECCV. So Dream Motion is the first framework that utilizes score distillation of text-to-video model for video editing. And in this work, we first question why is diffusion-based video editing challenging? So text-driven diffusion-based video editing presents a unique challenge that was not presented in the image editing scenario. So reconstructing temporally consistent and complex real-world motion throughout the reverse diffusion process, which starts from Gaussian noise. So the denoise video should not only have high fidelity to the target text, the editing text, but also should have high fidelity to the complex motion of the input video. So for example, this video depicts this video on the top depicts a flamingo walking on the grass, but lacks fidelity to the original video, the motion of the original video. So specifically, the problem is the ancestor diffusion sampling process that starts from the Gaussian noise, or at most DDIM inversion, inverted noise. And as a result, most other works supplement the reverse diffusion process by injecting attention features, integrating explicit visual hints like depth maps or optical flow, or overfitting the video model unit, the unit of the video model into the input video. However, all these expensive efforts can be eliminated. We believe it can be eliminated if we actually don't have to start from the Gaussian noise. So in other words, we propose to diverge from the standard ancestor denoising process, but instantly we want to directly edit the non-noisy clean level input video. And the way we achieve this is by score distillation sampling. So this figure illustrates the existing usage of score distillation sampling. So they usually leverage pre-trained text-to-image diffusion model for the optimization of a generator model or some rendering model to meet the given text-based constraints where it's denoted as y in the figure. And the generator model is usually non-pixel representations like nerve representation. However, instead in dream motion, we do not need an external generator or renderer. We parameterize the input video by phi, x phi, and optimize phi directly using the gradients of the SDS loss. So that being said, we start the optimization starting from the video that already exhibits real-world motion without any noise. Thus, we do not need to worry about establishing or generating like a realistic motion from the Gaussian noise. So, and also we use text-to-video diffusion model instead of text-to-image model, so that we can exploit the motion prior, the rich motion prior of the video model to obtain the temporally consistent gradients. So then the optimization progress will look like this ideally. So as you can see, the optimization keeps happening in the non-noisy clean video space, thanks to the score distillation. So to inject the appearance indicated by the target, so editing text, we extend the delta denoising score mechanism to distill video scores instead of image scores. So the upper branch is the reference branch, where we have an input video and a corresponding text, the text corresponding to the input video. And the bottom branch is the target branch. Initially, we copy and paste the input video, which is the optimization target, the red colored box in the figure. For both videos, we add the same noise, exactly same noise, and predict the noise using a frozen text-to-video model. But the difference is that in the reference branch, we have matching text input on the top, but on the target branch on the bottom, we have a mismatching text input, the editing text. Then semantically, this predicted noise in the top right, the epsilon hat, we have gradients toward denoising direction, but this predicted noise on the bottom, the epsilon, will have two directions, denoising direction and the editing direction, because the text input doesn't match the input video, the video input to the UNet. So the final gradients used for the optimization is simply computed by subtracting the top, subtracting the bottom by top. Then we have gradients, which is directed to changing lion to tiger in this figure. Then gradually the optimization target will be edited to follow the target text. However, this optimization alone raises a problem. So score distillation gradients are inherently noisy, and the inaccurate gradients accumulate structure errors throughout the optimization process. For example, you can check the ring areas of the edited videos here. Yeah. So I believe that this kind of issue happens because the available text-to-video model didn't have like a super strong generative prior or the motion prior. So to address structure integrity, which we focused on self-similarity descriptor, which is a representation that is robust to local texture patterns, yet preserves the spatial layout over layout and shape and perceives semantics of the objects and their surroundings. So the effectiveness of self-similarity-based descriptors in capturing structure while ignoring appearance, like a local appearance information, have been previously demonstrated in style transfer tasks using deep CNN features or image editing tasks using vision transformer features. And DreamMotion, this work proposed to use self-similarity through deep diffusion features. So in our framework, we first extract attention key features from both branch during the denoising step of score distillation. Then we compute self-similarity map using the extracted diffusion features from both branches and match the self-similarity maps across both spatial and temporal dimensions, which we call space-time self-similarity matching in this work. And thanks to the correction by self-similarity map matching, now we can generate videos without structure and motion errors. So these are editing results of DreamMotion. So especially for the red box edit case, we compare with other baseline on the next slide. So our method showed highest preservation of the motion and fidelity to the target text. This is another example. And this is another example too. And this is another comparison with the baselines. So in addition to DreamMotion, like I would like to share one another work called EMU edit, EMU video edit by Meta, which was also presented in ECCV this year. So if we were to do fully supervised model training solution for video editing, source and target video pairs are necessary, which are extremely hard to obtain because they simply do not exist in real world. So one can of course use off-the-shelf video editing methods to get this high expensive data set and do some data curation or other approaches like instruct pix to pix. However, like this EMU edit believed that distillation of multiple teacher networks could be another solution, alternative solutions to this, which does not require any fully supervised video pairs dataset. So for example, say we have a foundational text image to image model, so image editing model on top, which is relatively easier to get. And also a text to video model that shares the same spatial rates with the image editing model, but have temporal rates where they have the motion prior. Then distilling the scores of image to image teacher from the top will teach accurate editing capability, while the scores of the text to video model from the bottom will assure that student model keeps generating temporally consistent videos. And this is how EMU video edit trains their foundational video editing model without any supervised video editing dataset. So very lastly, I would like to share my latest project called Track4Gen very briefly, which I worked during my internship at Adobe. So this is not about controllable video editing or synthesis, but the main focus of this project is introducing dense point correspondence in video diffusion space. So since last year, generative priors in image diffusion models have shown to have strong 3D implications. Notably, pioneering works like DIFT demonstrated that correspondence can emerge in image diffusion models without any explicit supervision. These works typically extract diffusion features at specific time steps and layers of the unit, then perform a nearest neighbor search to establish correspondence. So following this trend, our natural question was, can we use video diffusion models instead for these 3D correspondence tasks? So since they're trained on videos, they should outperform image priors, which have never been exposed to videos during the training. So specifically, unlike existing video correspondence methods that typically extract features from videos on a frame-by-frame manner using image models, we believe that video diffusion models provide a stronger foundation for finding visual correspondence across frames. However, there isn't a single go-to choice for video diffusion models, unlike the case of image diffusion, where stable diffusion dominates. So we analyzed the features of 4 different video diffusion models highlighted in blue. So gyroscope, text to video, stable video diffusion, image to video, I2V XL, and also like recently trans-DIT based OpenSora. And let me jump directly to the conclusion. So we discovered all models commonly performed bad at dense video point correspondence task, also called video point tracking. So for example, here's a direct comparison between OpenSora features and DynoV2 features for the video point tracking of the foreground object of the this video. So as you can see, DynoV2 performs significantly better than the OpenSora features. And also it's worth noting that the OpenSora was the video model with the most temporally rich correspondence in its features among all the models we investigated, but still were bad compared to DynoV2 image features. So the next question naturally becomes, can we improve temporal correspondence of video diffusion features? And this question forms the core idea of our Track4Gen paper. And to achieve this, we first needed to understand how foundational video trackers are typically trained. So the specifics can get quite complex and are not uniform, but I provide a simplified overview of the very basic laws. So given a curry frame, TQ, the curry frame, and a curry point location, the curry point location is noted as PQ here, and a target frame, T. The goal of video tracking is to find the corresponding target point in the target frame. So first, video tracking is done using some rich semantic features. So for example, trackers use some foundational image model to encode the frames such as ResNet. Then using these encoded features, the large F, you extract the feature of the curry point, the feature vector of the curry point, Q, then you can obtain post volume, the similarity map by dot product between the curry point feature vector and the whole target frame features, large FT for the target frame features and the Q for the curry point vector. And a simple way to determine, so given this CT, the cost value map, a simple way to determine the target point in the target frame is doing argmax operation in the cost volume. But argmax is not differentiable, meaning that you can't backpropagate the loss. So instead, you do the differentiable soft argmax. So first, get the argmax location, the constant location, which is a constant, then compute weighted average using points within certain radius. So doing so results in the predicted location of the target point, the x hat and y hat. Then the loss is defined by simple regression between the predicted point coordinates and the ground truth point coordinates. And here the coordinates are usually normalized between -1 and -1 to 1. So using this tracking backpropagation algorithm, we first propose a hypothesis based on findings from recent literature on image diffusion models. So studies recently have shown that image diffusion models learn discriminative features in their hidden states, and that the better diffusion models produce better representations in their hidden states. More specifically, a recent promising work called RAPA demonstrated that improving feature representations leads to better regeneration outcomes in image. So we adopt the same philosophy, but see this with the temporal perspective. So we argue that feature level temporal consistency directly correlates with pixel level temporal consistency. So more specifically, tracking failures in diffusion features often coincide with appearance drifts in the generated video pixels. So by appearance drift here, we refer to a phenomena where visual elements gradually change unnaturally or mutate or degrade over time, leading to inconsistencies in the objects within the generated videos. So in contrast, when videos are generated using features that are temporally consistent enough to enable smooth tracking, the resulting videos are fully consistent. So this is another example. So take a closer look at the center part where the appearance drift happens in like the mid of the center part, where the tracking fails if the pixels in the pixel space there's inconsistency, and if there's no inconsistency, the tracking is completely smooth. So, and this is the Track4Gen training overview. So in addition to the standard video diffusion loss, we provide a track level supervision, the video tracking loss used in video tracking literature. But we use the diffusion features for the loss. So, and in our paper, we often call this loss as a correspondence loss. So regarding where we pick features and perform tracking, we use the third upsampler layer of the UNet backbone, which we did investigative which layer is the best, and also this choice is supported by like the literature on the image diffusion model. So the correspondence using image diffusion model. So because they are the same unit, and usually these video models start from stable diffusion, the image diffusion. So here, red in the figure, the red colored blocks represent layers optimized by the diffusion loss, standard diffusion loss, while green blocks are optimized by the correspondence loss. Blocks colored both red and green are influenced by the joint diffusion and correspondence loss. But since we decide to fine-tune from a pre-trained model instead of training from scratch, we make a small architecture change. So specifically, instead of directly using the raw diffusion features for the correspondence estimation, we propose a trainable refiner module RPi, which is designed to refine the raw features by projecting them into a correspondence-rich features space. So we call this refined features. Yeah, so the conclusion of this joint training framework is that this leads to improved video generation in terms of appearance constancy or appearance consistency, in addition to the temporary consistent video diffusion features. So we first qualitatively compare against the pre-trained stable video diffusion, the original stable video diffusion model. This is another example. And one could claim that maybe the improvement is coming from the data set we use for the fine-tuning. So we also compare with the fine-tuned stable video diffusion. So fine-tuned stable video diffusion means the stable video diffusion that is fine-tuned with the same videos from the data set as Track4Gen, but without any correspondence supervision or the correspondent loss on its features. And this is another example. And lastly, this is a comparison with Track4Gen trained without the refiner module, where we showed the additional network R5, yeah. And for all the comparisons, we show the quantitative evaluations in the paper. So we also compare the video point tracking performance against the original stable video diffusion and one additional video diffusion model, gyroscope text to video as a reference. So existing video diffusion models significantly lack video point tracking capability in their features, but Track4Gen enables accurate video point tracking thanks to the additional tracking supervision. This is another video tracking qualitative example. And we also conduct quantitative tracking experiments on several tracking benchmarks. So the video point tracking capability is also demonstrated when we investigate the features of the generative videos generated by Track4Gen. So when we analyze their features during the denoising process, specifically, we extract their features from the last denoising step and perform video tracking using nearest neighbor search. Then we could see that the tracks are correctly estimated, showing the feature space temporal consistency. This is another example. Yeah, so this is the end for Track4Gen, and also this is what I prepared for this talk. And yeah, so thank you for listening, and I would happy to get any questions or comments.
Yeah, thanks, Hanho. So, I have question regarding like in the first work,
Mm-hmm.
in ground A video, it seems there was a place, in the gated diffusion, like in the gated attention, self-attention, where you try to use like a Fourier preprocess for the
Yeah,
lake.
yeah, yeah.
I'm curious, is it actually a common practice, or you find it particularly useful to use the Fourier there?
It is just a practice that I didn't validate. It's like for this kind of literature in image, like you just use the Fourier encoding to turn these numbers, the coordinates to the tokens. So they just use it. So I just followed the practice. Yeah. Yeah. I
Oh,
think it's
okay.
from I think it comes from the nerve, like how they encode the locations to some,
Oh,
yeah, yeah.
it actually come from nerves?
Yeah, yeah.
Okay, okay.
And
I
also we use the same, like this is not trained, like so we use the pre-trained from the nerve
Mhm.
literature thing. Yeah.
Mhm. I see, I see.
Yeah.
So in the like so in VMC, if I understood it correctly, it would require like training for each single video, right? So
Yeah,
if
yeah, yeah.
to like edit, and then it also same applies to the like the dream motion.
So in BMC, so it is like a one-shot framework. So
Mm-hmm.
for each video, we have to fine-tune the backbone model for BMC. But for Dream Motion, so we basically make the video model frozen. Yeah, but we optimize the input video directly. So we do not in Dream Motion we do not require any model tuning. Yeah,
Okay, okay, no model tuning in
yeah,
motion, dream motion, but okay, I see, I see. So I wonder like in all kinds of method, um, so like score distillation, or maybe
mm-hmm.
like a motion vector optimization, or even inversion based editing method. Which one do you find the most efficient, and it would be like less computational expensive?
Mm. So actually, score decision is quite computationally cheap because so when we compute this loss, like for example the loss LSDS, so the trick, so the like thing like this is like the best advantage of score decision. So we do not have to how do I say, like turn gradients on this
Mhm.
UNet. So
Yeah.
just like when we do inference, like we do not have to turn on the gradients, so you can use like no grad and get these gradients and get these epsilons, and then just if you soft subtract these epsilons, then that is like the directly the gradients where we can use it to like optimize like whatever you parameterize. So I think score distillation is quite good at, yeah, like a very good choice for if you're like considering about the efficiency, yeah. And this is not really time consuming too, yeah.
I see, I see. Then like among like those methods, which one do you think would be the best?
Uh, I think, but for the efficiency, I think like my first work, like roundup video, is like the most efficient in terms of both time and memory, because like it's simply zero shot. You don't optimize
Yeah.
any latents and any model, but you need this pre-trained some trained layers in the middle, the gated attention, and this is could be understood too as like a model training solution using some right data set. But I think so it is quite hard to achieve getting these rates, but like once you get it, this is like the I think that is like the most practical work. Yeah. Yeah. And to my knowledge, like companies like Adobe or like video companies, they do prefer model training approaches over like one shot or like latent optimization approach. Yeah.
I see, I see. So how do you like what do you think of so in the current presentation, it seems like the latest editing works, they're focused on like maybe structural change or like a background change. How about like what if we want to do works on like motion change or maybe let's say like adding a new object in the scene and assigned a motion to it.
Yeah, so that is a very good question. So I think that is actually the trend, because like there are many works, not only my works, doing the appearance editing or like background editing or like those kind of appearance editing basically. But like so recently people are quite focusing on the condition called, so these kind of conditions, so tracks. So they given a video and some pre-trained video tracker, one can obtain like video trajectories of either dense or sparse trajectories. And people are using these kind of trajectory conditions to make a image to using an image to video model. So input video, I no input image, and some maybe some tracks using from other reference video, and then they use image to video backbone and do somehow use these track conditions to achieve like animating some static image with your intended motion. Yeah. Yeah.
Yeah, like the Tora works, right? Like
Yeah.
they're
Yeah. Yeah. Yeah.
conditioning on the trajectories.
Yeah. Yeah.
Mm. Yeah, like I also have like one final question about the personalization. So I think Pika's lab recently just released like 2.0, and then they
Mhm.
have like a uh feature that they were able to add ingredients into the video. Yeah, like I was actually very impressed by that, and then they said they're not doing this by law, and then it seems they were able to inject any kind of objects in any numbers into the video generation.
So actually, I think I've seen the demo of that, but I haven't used it. So by injecting ingredients, so it's like, yeah, like there's like an input video and like a video of like for example a man like sitting, and then you can like input like some yellow hat, and then the man will do the same thing but with a hat, right? It's like that, right?
I think for their current feature is only for video generation, so no video editing yet. But I
Ah,
think
okay.
yeah, I think it would be like a good idea to explore in this direction. Maybe like editing, but you get the control on what subject to add. Yeah, I think in image domain we already have some work like this, like the dream edit from our lab,
Mm-hmm.
uh, where we focused on image and add certain subjects in it. Yeah, I
Mm-hmm.
think it would be very cool if we can also look into this kind of method.
Yeah, I think so. In the dream edit, do you use like some curated data set, like or
Yeah, for dream edit, like because that was like the early exploration work, so we were relying on the dream booth models
Mhm.
to do this kind of stuff.
Yeah, yeah, that's like a cool work. But I think for the Pika, I think they probably made their own data set, like ingredients as input
Hmm.
and like because they have to make it like they make to make it a product and it requires like latency. So like they
Hmm.
probably made the pair of data set, video data set. Yeah.
Hmm.
Yeah.
Okay, I see, I see. Yeah, like okay, I'm gonna pass to other people. Uh,
Yeah.
Wei Ming and Dongfu, do you guys have questions? Okay, maybe not.
Mhm.
Yeah. Okay. Let me stop the recording first.